this example, we're going to look at the discovery of the electron and think back to the early days of particle physics. A natural question you could ask is an electron the same thing as a proton, just with the opposite charge, or does it have more differences between the two particles? So the way this question was addressed is, let's begin by taking two parallel plates, and we'll set those plates to be kind of close together, and we're going to set up a uniform electric field between the plates. So we're basically charging up a capacitor. So here are my two plates. I'll say that the plates have a length L, so here is x equal to 0, and here is x equal to L. Now, I am designing this experiment and building the materials for this experiment, so I'm allowed to, I have this under my control. Now, we're going to set up a uniform electric field between the plates. We basically just built a capacitor. And we learned previously that a capacitor is actually a very simple device. It's just two parallel plates, you put some charge on it. So presumably you have access to batteries, you have access to metal plates, so you could control how much charge is on the capacitor. Now, what we're going to do is we are going to send in some electrons, so we'll get a source of cathode rays, and we're going to send these electrons through. So the electrons will come in from really far away, they'll come in, and then the electrons will pass between the plates. If the electric field is turned off, the electrons will just pass between the plates and continue on. But when we turn on the electric field between these plates, the electrons will see the electric field and they'll be deflected upward. While the electrons are between the plates, they're going to feel an upward force because we have F is equal to QE. And after the electrons exit between the plates, there is no more electric field out here, so the electrons just then continue up on whatever their final velocity was. So I could say that the electrons had components for their initial velocity. So I could say they had initial velocity components. Vx and 0, and they had final velocity components. Vx and Vy. The electrons did not feel any force in the horizontal direction, so the initial velocity in the x will be the same as the initial velocity in the y. There was no acceleration in the x direction, so the velocity in the x direction is going to be unchanged. Initially, the electrons were not moving in the y direction, but the electric field pushed upward on the electrons, and that caused them to accelerate upward. And at the end, they will have some final velocity of Vx in the horizontal and Vy in the vertical. From F equals QE, we know that if we're dealing with a negative charge, the direction of the force will be opposite the direction of the electric field. Because the electric field points down, I know the force on the electrons is going to be pointing upward. Now, F net is equal to MA, so I could write that equal to MA. And because the direction of the force is upward, I could write, if I want to lose the vector symbols, I have the upward force is QE is equal to MA. So I could write the acceleration of the electrons as being QE over M. So this is the acceleration upward of the electrons. where here Q is the charge of the electron, M is the mass of the electron, and E is the strength of the electric field. So one thing I want to point out, Q and M are properties inherent to the electron. These are properties of the particle we're trying to learn about. E is the electric field, and that is a number that I am very much in control of. I know how to set up an electric field between capacitors because we have V equals ED. I know the distance between the capacitors. I could get a certain battery. E is very much within my control. So what we're going to do now is let's put this idea on the side for a moment. Let's set up a magnetic field between the plates. And we're going to have the magnetic field cancel the effect of the electric field. So now let's set up a magnetic field pointing into the board. And if I do that, I will have my plates right there. I will have my electric field pointing downward. So here's my electric field, E. Here's my magnetic field pointing into the board. Given by B. And we found before that the electrons are pushed upward by the electric field. What direction will the magnetic field push on the electrons? To find the direction of the magnetic force on the electrons, we use the right-hand rule. So the electrons are coming in from over here. Previously, with the electric field only, they were deflected upward and continued on out of the plate. Okay, so the direction of the electron's motion is to the right. I'll have my forearm aligned to the right. Now the magnetic field we said is pointing into the board, so I make sure my forearm is still pointing to the right, but then I pivot my forearm and my four fingers could curl into the board. When I raise my thumb is pointing upward, but I remember that an electron is a negative charge, so the direction of the force on the electrons due to the magnetic force is going to be downward. So the electric force, F electric, pushes up, and the magnetic force, F magnetic, pushes down. Now, we did not yet talk about how would you set up a uniform magnetic field in a region. Think back to when we talked about setting up a uniform electric field in a region. It turns out it's very simple to do that. You just need two metal plates, you put charge on the plates, and right away you have an approximately uniform electric field. We will learn at the end of this chapter how you would go about setting up a uniform magnetic field. It turns out it's a very easy thing to actually accomplish. It's a very simple setup. So for now, let's just trust that we have a uniform magnetic field. The direction of the electric force is up, the direction of the magnetic force is down. Let's tune the strength of the magnetic force so the two forces cancel perfectly. So let's set F electric plus F magnetic to be equal to 0, so that they cancel exactly. Well, when we do that, we've had that the electric force was given by F equals QE. So the electric force was QE, that was pointing upward. The magnetic force was QVB sine theta, so that was downward. So QVB sine theta, and we want the forces to cancel. Now, theta is the angle between the direction of motion, the direction of velocity, and the direction of the magnetic field. The electrons are moving to the right, the magnetic field is into the board, the angle between those two quantities is 90 degrees, and the sine of 90 degrees is just 1. So this is actually going to be equal to sine 90, which is just equal to 1 anyway. So positive quantity because an upward push from the electric force, negative quantity because a downward push from the magnetic force, and these two forces cancel, so they sum to 0. So I could write then QE minus QVB is equal to 0. I also included the subscript Vx here because that's the electron's initial velocity in the x direction, and this number never changes. Now, okay, I have Q and Q cancel each other out, and I could rearrange this term and find Vx is equal to E over B. Okay, this is going to be one important piece of information for discovering the electron. We found if the electric force and magnetic force cancel perfectly, the speed of the electron is going to be related to the strength of these two fields. Okay, let's turn off the magnetic field. Let's have just the electric field again. We're going to keep this result close by. We'll be using it very soon. So we found that Vx is E over B. So if we turn off the magnetic field, we are back to this scenario where we have our capacitor plate with no more magnetic field. We still have the electric field, so we still have our E. And from x equals 0 to x equals L. And we said the electrons come in with an initial Vx, Vy was 0. And then the electrons are not going to just pass straight through, they're going to be deflected upward, and they exit with some final velocity. Vx is the same, and Vy. So what we want to do is we know the value of Vx. Vx was E over B. Let's ask the question, what is this Vy going to be? So finding Vy is going to be our goal now. So if I want to find the vertical component of the electron's final velocity, I could think back to some courses from 121 and say, well, Vy is V initial y plus AYT. Okay, V initial y was 0. It was not moving up or down. It was just moving to the right. And then we had, in this scenario, when the electric field is the only force on the electron, we have F is equal to QE, and F net is always equal to MA. So we found A was QE over M. So if we find the amount of time the electron spends between the capacitor plates, we will then have enough information to determine the length, the acceleration, and the final velocity of the electron. So to find the length of time between the capacitor plates, I could say x final is equal to x initial plus v naught xt plus 1/2 axt squared. Okay, throughout this problem, there is no acceleration in the horizontal direction. All the acceleration is in the up-down direction. So ax is going to be 0 throughout this problem. X initial is the time you begin passing between the plates, so that's 0. X final is going to be L. So X initial is 0 as well. So what I find is L for my X final position is 0 plus Vx times t. So I get a Vx times t. Vx is the same as V initial x, which is going to be E over B. The electron never changes its speed in the left-right direction. So I could say that from this equation, the time the electron spends between the plates is going to be equal to L over Vx, which is going to be L over E over B, which is going to be LB over E. Now let's think about what this problem, what we found for a moment. The strength of the electric field, that is something that is in my control. I'm free to set the strength of the electric field because I attach the battery to the plates. I know how much charge is going to be on the plates. The strength of the magnetic field, I'll just promise you right now, that is something very easy and within our control to set. And L is the length of the plate. So L is how big I chose to make this capacitor plate. That's also something under my control. So I am fully in control of how much time the electrons will spend, or I could easily measure how much time the electrons spend between the plates. I just tune the value of E and B just right so they tend to end up canceling each other. So now I know the length of time between the plates, I know the acceleration of the electron, so I could find the y velocity of the electron. So I could say the final y velocity of the electron is going to be ay times t, so I get a QE over m times an LB over E, and I get Vy is going to be, okay, E and E cancel, QLB over M. So we have Vx and Vy. So what am I going to do with this information? So we have Vx is E over B, Vy is QLB over M. I am also able to measure this angle theta. Now, I'm only zoomed in. The full experiment, you would have, if I were to build this experiment in its entirety, I would say I have a beam of electrons coming in. I have two metal plates, just like that. The metal plates are small and kind of close together. So the beam of electrons come in, they're deflected, and then way out here, far away from the plates, I have a phosphorescent screen. So when the electrons hit the screen, the screen will glow. So you'll get some glowing on the screen over here. And when I turn the magnetic field on, the electrons will just hit pass right between the plates, and the screen will glow right here. And so it is relatively easy for me to measure this angle theta. Now this angle theta, the angle between where the electrons hit the screen when they're undeflected and where the electrons hit the screen when you have the electric field only, is going to be the same as the angle of this velocity vector. You have your Vx and your Vy component. You break the vector into its components, you could find the angle between them. So I could say that tangent of theta is going to be Vy over Vx. And so I could say tangent of theta is going to be QLB over M over E over B. And if I want, I could then rearrange this equation, and so I could get tangent of theta is going to be, we have Q over M times L B squared over E. And this is my result. This is just fantastic. Okay, so why is this result interesting? What are we actually seeing here? There's a reason I decided to write this result in this particular form. Let's think about Q and M. Q and M are the mass and the charge of the electron. So Q and M are the mass and charge of the electron. These are properties that are inherent to this particle itself. Now, what else do we have in this equation? Theta is the angle that of the deflection. That's easy to measure. Because I just have a phosphorescent screen. I mark the angles on the screen, and I'm just careful. That is not really that bad to measure. What are the other quantities? We have an L, a B, and an E. Well, L is just how big I made the plates. So L is the size of the plates. And that is something completely within my control. So I know how big the plates are because I built this experimental setup. And the other two quantities, E and B, the strength of the electric field and the strength of the magnetic field, these are under my control as well. I have two capacitor plates. I know their size and their area. I know the voltage between the plates because I set up a battery connecting the two plates. I know the strength of the electric field. By a very similar line of reasoning, I know the strength of the magnetic field. So these I know. So in this problem, the only unknowns are Q and M. So Q and M are something that I am learning about the electron. So if I wanted to, I could shoot electrons through between these plates, and I could find the ratio of charge to mass for the electron. Now, is a proton the same thing as an electron, just with the opposite charge? Well, if that were true, you would expect the exact same result. So if I rearrange this equation, I could say for the electron, Q over M is equal to, I build this experiment, LB squared over E tan theta. If a proton is just a heavy electron, I should get the same value for Q and M. I should especially always have the exact same deflection. But if a proton is not just a heavy electron, if a proton is a particle that actually has a different mass, well, if M is much bigger for a proton, then this term is going to be much, much smaller. And so I could say for an electron, we get something. We get some angle of deflection when B is turned off. For a proton, if a proton has a larger mass, then you would expect this number to be much smaller. So if this number is going to be smaller, I need tangent of theta to be much bigger. So in this case, we should have a much greater deflection if the electron is going to be, if the proton has the same charge but more mass. So if that's the case, for a proton, we get a greater angle of deflection. If M is greater. So you could actually run this experiment, and if you were to run this experiment, you would see you get some amount of deflection for an electron, a lot more deflection, a much bigger angle of deflection for a proton. So that suggested that the electron is not just a heavy proton. An electron is actually a different type of particle with its own properties. And today we know many more ways in which the electron is different from the proton, not only by charge, same but opposite charge, and a different mass, but it has other properties like different lepton number. A proton is a composite particle made of quarks. An electron might be composite, but we don't know if the electron is actually fundamental or not. So this was an early experiment that basically discovered the electron is not just a heavy proton.